Hello, I'm Charlie Dickens, and I will be presenting the work on subspace exploration and projected frequency estimation. This is joint work with Graham Cormode and David Woodruff. If you take nothing else from this presentation, I would like you to be aware of the following points. Number 1. First, we introduce projected frequency estimation. This can be thought of as column-restricted versions of frequency estimations over n by d binary arrays. The trick is that columns are revealed after observing the data. Secondly, we show that these problems are hard. Typically, they require 2 to the omega d space for constant factor approximation. However, we also complement these lower bounds with upper bounds that are polynomial approximations in n to the order c space. Here, c can be thought of as being a small constant. This is better than enumerating a sketch for every column query. In standard streaming, we have the following setup. A sequence of items are revealed one by one and used to populate a frequency vector. We then ask for statistics of the frequency vector, such as the number of distinct elements, the f0, or perhaps the LP norm in the bottom right-hand corner of the slide. We will be interested in similar functions, but over different inputs. The inputs we are interested in are binary tables such as the following on the slide. For example, has user I seen advert J? And we can characterize this over many users and many adverts. But now suppose we are only interested in adverts 3 and 4. Then user 1 has viewed advert 3 and advert 4, likewise the same for user 3, but user 2 and user 4 have seen neither. This encodes the frequency vector 2, 2, and the f0 on this frequency vector is 2. On a different column query, we see different patterns, and here all length 2 binary strings are present, so the frequency vector is the all ones vector. This means that the f0 on this frequency vector is 4. This type of behaviour explains exactly the setup of our problem and the crux of the model. Columns are revealed after the data is seen. If this were not the case, then we could map to a standard stream and use any streaming or sketching algorithm which is suitable for our query. So you might be wondering why we are interested in projected frequency estimation. We might be given a large data set and want to understand the bias or diversity on certain features. That is, can we understand how well certain groups are under or overrepresented on certain given features? This might also have implications for different types of clusterings or later analysis that we want to perform, again, on different subsets of the features. Now I'll move on to the lower bounds. Mostly, these will follow from the index problem. For those of you not familiar, the index problem is as follows. Alice holds a binary vector A, and Bob holds an index I. Bob is tasked with outputting AI following communication from Alice. It's known that omega n bits are needed to be transferred from Alice to Bob for him to output AI correctly. We will use this setup to generate hard instances and reduce to the index problem. Our lower bounds can be summarized as follows. We obtain space lower bounds of 2 to the omega d for constant factor approximation. The specific problems that we study are count distinct, FP estimation, heavy hitters, and LP sampling. The proofs for items 2 to 4 is very similar as for item 1, the count distinct. However, the calculations are more involved, so I will just outline the idea for the count distinct proof. Typically, the proofs have the following outline. We sample a code C of length d and weight k. This code will be exponentially large. We will often exploit properties of the code, such as two words from C sharing a 1 in at most a certain number of locations. That's a parameter for us to choose. Alice will hold a subset T of C, and her vector has a 1 in this location if she holds the word for a given location, otherwise it's 0. Also, we need a lifting function, star q. This maps a single word x in T to many, many child words. Again, q is now a parameter for us to choose. Bob holds y in C, and he must determine whether y is in T or y is in C minus T. So here's the idea for F0. From C, Alice will be given a set T of code words. She will apply star q to all of the words that she holds in T. Recall, this is the definition of star q, and you can see that for any code word x, star qx generates q to the k child words. So here's an example: x equals 1100, q equals 3, and these are the type of child words that we would see in the table. Alice will populate the input table for the algorithm with all the patterns star qx that she holds. Bob will hold a y, and this is the crucial point. He will query the columns on S equals the support of y. This isn't the proof, but it gets to the idea of what we do in the proof. So now suppose Alice only holds 1100, and the input table is star 3x. If Bob holds y equals 0011, then the support of y is 3, 4. So on this part of the table, he would mostly see zeros or few patterns. Alternatively, if Bob holds 1100, then the support would be 1, 2, so he would see many patterns. We can generalize this further. If Alice does not hold y, then the algorithm should return something like few patterns. If Alice does hold y, then the algorithm should return many patterns. Now, overall, we can use this reasoning to show that an approximation factor of q over k can distinguish between the two cases for index. We can show that the code we use is large, and in the paper we demonstrate how to trade off between q and k to get the 2 to the omega d lower bound. Similar ideas are used for other problems that we study, such as FP estimation, heavy hitters, and sampling. The codes that we use are slightly different, but the argument is very similar. The FP estimation results and LP sampling mostly follow from heavy hitters, but again with mildly different calculations. This table, I don't want to go into the details of it, but shows how the arguments are related and the different maps that are applied. For those interested, we also show dichotomies between classical and projected frequency estimation problems. Now I'll move on to upper bounds. We will introduce a tool called an AlphaNet. This AlphaNet contains all subsets of size d whose size is at most d over 2 minus alpha, alpha d, or at least d over 2 plus alpha d. We can use alpha to control the size of the nets through the binary entropy function. Now the binary entropy function is at most 1, but it can be much smaller. If you look at the graph in the bottom right hand corner of the slide, you can see that as t is smaller, the entropy function is smaller. An example of the net is shown here for d equals 6 and alpha equals 1/6. This means that we keep all sets of size at most 2 and at least 4. However, no subsets of size 3 are included. For larger d, this means we rule out subsets in the middle of the power set lattice. Note that as d gets large, it is this central portion that contains a significant fraction of the mass. How do we use an AlphaNet in the algorithm? Well, suppose that we're given input data A and a column projection query S. Remember that the column projection S is not revealed when I observe the data, it's revealed afterwards. So first of all, we observe the data and instantiate a net N. In the net, we will initialize a sketch for every column subset. When the set S is revealed, if it's in the net, then we return the estimate from the net. If it's not in the net, then we will round S to an alpha neighbour in the net and return the estimate for the alpha neighbour. An alpha neighbour simply means that the symmetric difference is bounded above by at most alpha d. This allows us to control the deterministic distortion in returning estimates on S prime rather than S. And this is characterised through the following lemma. The main point to take away from this is that the count distinct can be the distortion on the count distinct in using the net is 2 to the alpha d. You can think of this as having binary words over k columns. Then if we add a new column, we can possibly double the number of binary strings if we have sufficiently many rows in the table. On the other hand, if instead of k columns I have k-1 columns, potentially I could halve the number of binary strings that are observed. And then taking n equals 2 to the d, we achieve the claim that I made on the first slide. So just to illustrate what's going on here, we have the relative space on the left-hand side. This is the fraction of sets stored in the net divided by the size of the power set. As alpha increases, I store sets increasingly further away from the center of the power sets, meaning fewer sets are stored. Storing fewer sets means the approximation factor increases, and here I've plotted 2 to the alpha d, which is the dominant term in the approximation factor. On the right-hand side, I've plotted the approximation factor and space trade-off. Here we see that reducing space by a factor of 4 gives an approximation factor on the order of tens, and reducing space by a factor of 256 gives an approximation factor on the order of 100s. Thank you for listening, and I look forward to your questions.